Everything you've ever touched, seen, or measured, your body, this screen, the air you're breathing, might not be made of matter at the deepest level. It might be made of something stranger, something more abstract. Physicists have a word for it: information. And the argument for why that might be true starts with a question so simple it sounds almost childish. Yes or no? That's the whole thing. Yes or no? Because if you strip quantum mechanics down far enough, that's what keeps showing up. A question is asked, a result is recorded. One of two answers comes back. And some physicists, especially John Wheeler, came to think that this was not just how we learn about reality. It might be what reality is made of. That sounds absurd. It also gets harder to dismiss the more you follow where quantum mechanics leads. In the first video, Double Slit showed that particles don't behave like tiny pebbles with fixed properties just waiting to be revealed. In the second, Heisenberg showed that quantum world isn't built on sharp classical certainty. In the third, Bell showed Einstein's hidden classical reality couldn't survive experiment. And in the fourth, we saw that even after all that, physicists still can't agree on what quantum mechanics means. But all of those videos had one strange thing in common. Every result depended on what question you asked. Every outcome came back as an answer. This detector or that one. This setting or that one. Yes or no. And once you notice that pattern, a new possibility opens up. Maybe that isn't just how we interrogate reality. Maybe that's the basic structure reality is built from. That was Wheeler's idea. And Wheeler wasn't some fringe thinker saying weird things from the sidelines. He works with Bohr. He worked with Einstein. He supervised Richard Feynman. He helped popularize the term black hole. He introduced quantum foam. Late in his career, he became obsessed with a question that sounds philosophical until it starts swallowing physics. What if information is more fundamental than matter? Wheeler's answer became famous as a slogan: it from bit. Every it, every particle, every field, every physical thing derives its existence at bottom from bits, from yes or no distinctions, from answers to questions. And Wheeler didn't mean that as poetry. He meant it as a literal possibility about the world. Now, before that can sound like anything but vague sci-fi, we need to clear up one huge misconception. When physicists say information, they don't mean gossip, tweets, books, or files on a hard drive. They mean something much more basic. Information is the answer to a question. More precisely, to a question with distinguishable alternatives. In Shannon's information theory, one bit is the amount of information carried by a yes or no choice, one binary distinction. So if I ask, is the light on, that's one bit, yes or no. If I ask, did the detector click, that's one bit, yes or no. If I ask, did this particle come out spin up or spin down along this axis, again, one bit, yes or no. That may sound almost too simple, but quantum mechanics keeps dragging us back to exactly that structure. You ask the world a question in the form of a measurement. The world gives you an answer. And once that answer is irreversibly recorded, something changes. That's why information became so important. Because in quantum mechanics, information is not just something we collect after the fact. It seems tied to the actual structure of what becomes real. Now, take the next step. Classically, a bit is 0 or 1. You can copy it, store it, duplicate it as many times as you want. A qubit is fundamentally different. Before measurement, it exists in superposition, and an unknown quantum state cannot be perfectly copied. That's the no-cloning theorem. Quantum information isn't classical information wearing strange clothes. It behaves differently at the level of physical law. Then add entanglement and things get stranger still. Entangled particles do not just share a common history, they share a state. The information in that joint state cannot be broken cleanly into two separate local packets, one carried here and one carried there in the old classical way. That's why Bell's theorem mattered so much. Bell showed that the correlations seen in entanglement cannot be explained by locally stored classical information alone. The information structure of the quantum world is irreducibly non-classical. And now Wheeler's idea starts to look less crazy. Because if every quantum measurement is at bottom a structured question with a structured answer, if entanglement tells us the world's information structure is deeper than classical matter alone can explain, if even the properties of particles seem to depend on what question is being asked, then maybe information is not something we extract from reality. Maybe it's what reality is built from. Now take that idea to the place where physics becomes rude: black holes. You throw matter in, gravity crushes it, and according to Hawking, black holes are not eternal. They slowly evaporate, which leads to a terrifying question. What happens to the information about everything that fell in? If that information truly vanishes, then the most fundamental rules of quantum mechanics break down. That's why the black hole information paradox matters so much. It isn't just a weird puzzle about exotic objects in space. It's a stress test for whether information is fundamental. And the broad lesson most physicists now lean towards is this: information does not truly disappear, not even in a black hole. The details are still brutally hard, but the direction is clear. If black holes can't destroy information, then information is not just bookkeeping, it's something deeper. That is Wheeler's idea pushed right to the edge. Matter can fall in, energy can scramble, geometry can twist itself into madness, and still the information has to survive. That is an astonishing shift in viewpoint. The old classical picture says matter is primary, and information is something we read off matter by measuring it. The Wheeler-style picture says information is primary, and what we call matter is what information looks like when it takes physical form. Now, to be careful, that doesn't mean the universe is literally a laptop or a simulation running on somebody else's desktop. It means something stranger and more serious. Physical reality may arise from networks of distinctions, registrations, and yes or no facts more fundamentally than from little lumps of stuff. And that's where the previous videos all point. Double Slit suggested that properties are not simply sitting there classically before the question is asked. Heisenberg suggested the world is not built out of perfectly sharp classical quantities. Bell suggested local hidden classical structure does not recover what the world actually does. And the interpretation fight suggested that physicists still do not agree on what sits underneath. What if all those roads keep converging is because they're pointing to the same thing? A universe where questions and answers are more fundamental than matter and motion. And this isn't just philosophy anymore. Quantum computing works by controlling quantum information, superposition, entanglement, interference in ways ordinary classical bits can't. Quantum cryptography uses no cloning and entanglement to build security that depends on the structure of physical law itself. Quantum error correction is really about protecting fragile quantum information from noise and decoherence, not just protecting matter, protecting the informational structure encoded in a quantum state. And at the far frontier, some of the most ambitious physicists now seriously explore whether space-time itself may emerge from patterns of entanglement and quantum information. That isn't settled physics, but the fact that physicists are seriously asking whether space-time and entanglement might be the same thing tells you how far information has come. It is no longer a side topic. It is now one of the leading candidates for what reality is made from. So what does all this mean? It means Wheeler's old question is no longer just a poetic line from a famous physicist. It is a live possibility. If information is conserved more deeply than matter seems to be, if black holes can't erase it, if entanglement and no cloning show that quantum information behaves unlike anything in ordinary experience, if the world keeps responding to measurements as if answers are more fundamental than the classical objects we thought were carrying them, then the idea that the universe is made of information stops sounding like a metaphor. It starts sounding like a serious possibility. And that leaves one final problem, maybe the deepest one yet. If every physical fact comes from a yes or no answer, if reality is built from information, then who or what is asking the questions? That is where this story goes next. If you found this useful, a like and subscribe helps us keep making more of these videos. Thanks for watching.